Fractals are infinitely complex patterns, self-similar across different scales, and created by repetition through an ongoing feedback loop. This fractal was produced through a computer-calculated equation, repeated over and over at smaller scales. It's classified as part of the Mandelbrot set. However, not all fractals are this abstract. Examples of naturally occurring fractals include the branching of neurons, hurricanes, radially symmetrical flowers, spiral galaxies, and lightning. Fractals are also evident in the imagery created by kaleidoscopes. In mathematics, the fractal depictions of greatest note are the Sierpinski triangle and Pascal's triangle, which you may recognize. In music, the primary exemplification of fractals is demonstrated through fugues. A fugue is developed with the establishment of a singular melodic line or theme. The composition then goes on to incorporate simultaneous branching variations and repetitions of this line through counterpoint. The original theme may be altered slightly as it is passed between voices or parts. This branching process is nearly identical to the repetitive development of a fractal. The next video is a portion of a lecture from the Santa Fe Institute, which helps to further illustrate this concept.
Johann Sebastian Bach loved to play with symmetry. In his fugues, the theme is repeated many times in different forms. In the fugue we're going to perform tonight, listen for this theme in the horn. Now listen for the upside-down version of it in the second trumpet. The slowed-down version in the first trumpet. And the extremely slowed-down version in the tuba. Now let's hear how he puts it all together, complete with a great visual of this fugue.
Now that you've seen the elements of a fugue visualized in colored patterns, let's see if you can identify the transfer of the main theme in Bach's Little Fugue. Even if you can't read music, you've probably heard this before and will be able to pick up on the shifts between the first, second, third, and bass clarinet lines. The lowest resonant frequency of a vibrating object or an object in oscillation is called its fundamental frequency. A harmonic is defined as an integer multiple of the fundamental frequency. A wavelength of a single frequency forms a sine wave as a function of distance as it travels. If you consider this function in comparison to a fixed portion of a straight line, you can assign one wavelength to equal the whole segment. As the degree of the harmonic increases, the wavelength becomes shorter, and the line segment is divided more times.
A chromatic scale divides an octave into 12 equal parts. An octave is a ratio of 2 to 1. Suppose you have a string tuned to 440 Hz, which is the universal A. If you make the string twice as tight, the string will sound an A as an octave higher. The new sound will vibrate twice as many times. A fifth is a ratio of 3 to 2. If we start with an A at 440 Hz, a fifth up is E at 660 Hz. We can go up by fifths and down by octaves to produce every note in the chromatic scale. For example, if we start at A, which is 440 Hz, and go up to a fifth, we get E. Another fifth up, we get B at 990 Hz. If we take the B down an octave, we get B at 495 Hz. Next, we go up a fifth to get an F sharp. This progression of notes is called the circle of fifths. Another approach is increasing the pitch a half a step in the chromatic scale. This involves increasing the pitch by a ratio R. Since we do this 12 times to go up an octave, R to the 12th power must equal 2. To find R, we must take the 12th root of 2. Knowing the 12th root of 2 lets composers write in all different keys. Before mathematicians could do this math, they could only write music in certain keys.
This is the open A string on a viola. It's tuned at a frequency of 440 Hz, which is the standard agreement of what the pitch A sounds like. The harmonic above this A is one octave higher. This pitch is also an A, but is a frequency of 880 Hz. The string on the viola is divided into 2 equal parts. The next natural harmonic is the octave plus a perfect fifth above the original pitch A. This note is an E played at a frequency of 1320 Hz. The string is now subdivided into 3 equal parts. The final harmonic is an octave plus a fifth plus an additional fourth, which is now 2 octaves above the original pitch. This is, again, an A with a frequency of 1760 Hz. The string is now essentially divided into 4 equal parts.
Now you'll hear a 1-octave chromatic scale, starting and ending at the pitch E. As the scale ascends and descends, you'll hear the half-step intervals denoted by the 12th root of 2.
First, we must establish the relationship between the golden ratio and the Fibonacci sequence. It's easiest to visualize the golden ratio through the golden rectangle. We draw a rectangle with dimensions x, y. If we divide the rectangle at a point such that length y has a segment equal to x, the remainder of the line will be equal to y minus x. The golden rectangle now consists of a square and another golden rectangle. The proportion that illustrates this result is y over x is equal to x over y minus x. This process can be repeated again and again to further divide the area into more squares and golden rectangles on increasingly smaller scales. The Fibonacci sequence is defined as one where each term is determined by the sum of the two preceding terms. In this sequence, the limit of the ratio of each pair of consecutive terms is the golden ratio. The approximate value of this limit is 0.618. Because a sub n minus 2 equals a sub n minus a sub n minus 1, we can substitute these terms for x and y in the original scenario.
In the Hallelujah Chorus from Handel's Messiah, which consists of 94 measures, one of the most important points is the entrance of the trumpets at measures 57 to 58. These measures are 8/13 of the whole, or 0.618. Similarly, after 8/13 of the first 57 bars, we have another important point of the theme, the kingdom of glory. A third example is 8/13 of the last 37 measures at measure 79. This is the placement of "and he shall reign." It is unknown if Handel chose these locations deliberately, but this phenomenon outlines the golden section in music.
The next three excerpts will play samples of the Hallelujah Chorus, highlighting the events that occur at each pivotal shift in the music, spaced according to the intervals indicated by the Fibonacci sequence.